Welcome back to Let's Code. I'm Chris Biscardi, and today we are back talking about compute shaders once again. Here we have an example that is running a compute shader that generates simplex noise, three-dimensional simplex noise, with a time component, and then renders that to a 2D sprite, which eventually is picked up by the camera. Now, this compute shader builds on top of the compute shader that we talked about in the last compute shader video, which I'll link in the description. So give that a watch if you are interested in compute shaders in general, because this video is going to be about extracting the time component and sending it to the GPU in a buffer alongside all of the other data that we already have set up. So if you didn't watch the other video and you're not going to, then basically what we have here is the game of life example from the Bevy repo, which I've converted to add time to, and in addition, modified the shader to actually just be simplex noise, basically. So the way that our shader is set up is it's got an init phase or an initialization phase and an update phase. The initialization phase runs once, the update phase runs all the time. So I think today that we're going to start with the actual shader itself, and then we'll work backwards and we'll go into the Rust code that powers it. Because it's a little bit hard to understand what the Rust code is doing or why it's doing it if you don't understand what the shader is using it for. So in this case, we have this texture here. This texture is, first of all, our first binding, group 0, binding 0. 0 is just an ID in this case, so could really be anything. In this case, it's 0. This texture, we get read-write access to. So normally in like a fragment shader or something like that, you might have read access to a depth texture or a metallic texture or roughness or something like that. Or even just like the albedo, the color, the base color of the object. In this case, we have an image that we initialize on the Rust side and then bind to on the Rust side, and we pass it in here. So basically, we initialize this texture, which you can think of as a two-dimensional image, so like a PNG file. We fill that up with basically 0 values, so it's all like white or black or whatever. And then we write to this texture in our init phase right here, and we write to this texture in our update phase as well. And at the end of each of these, we call texture store, which writes the color information at the coordinates that we're given back into the texture. So the RGBA U norm is basically a vec4 of F32s. That's kind of the data representation for each of the pixels in this texture. And of course, we get read-write access to it. Below that, we've bound a buffer on the Rust side to give us time. So we define basically the way we're going to take the data out of that buffer. In this case, we define a struct with the time since startup in seconds, which is an F32 for us. This happens to come in, again, group 0, so same group, or same bind group, that is. And then binding 1 instead of binding 0, so it's the next thing, basically. This is a uniform, so contrary to what's happening with the texture where we have read-write access, this uniform is a value that just gets copied to all the work groups and then read, but not written to. So we aren't writing time from inside the compute shader. Bevy is sending us the time to read. And we set the time value to the time struct, which has this field inside of it. We only have the one field, which is fine. We could put more in here. We could put more bindings in here. We'll go over that on the Rust side later. Then we get the compute shader life cycles, basically. We have an initialization life cycle and an update life cycle. Well, work group sizes are 8 by 8 by 1. In this case, what that means for us is that we get 8 by 8 squares of pixels to work in. As far as I understand it, the work group size is basically the chunk of data that gets read in a batch and sent to a particular GPU node. So in our case, this looks a lot like a fragment shader. We get the built-in global invocation ID. The invocation ID, in this case, the global one, gives us what is effectively an XY position for a pixel in the texture that we have up here. We also use the built-in num work groups, although I've removed the logic that actually uses that. I just left it around for posterity, basically, in case I wanted to use it. So we need a location here to treat as sort of the XY position in our texture, so we know which pixel we're working with, or in this case, we're actually going to call it a texel technically, but we can think about this as a pixel. So we've got an X position and a Y position. We coerce these to an I32 because by default, they are a U32. We put them into a vec2 and we store that in the location variable. Now we need F32s for the noise, so I do exactly the same thing, except I use F32s instead of U32s or I32s. In this case, we also access the time since startup. I'm multiplying each of these values by some sort of smaller number so that we get smoother noise. So you can see on the left-hand side that we actually have like kind of smoothish noise. If I were to do something like make these both 10, nothing would happen because we're in the update function. Yes, obviously. Okay, let me do that down here quickly. So we use basically the same logic in both places. But if we make these 10, then you can see that this gets far more granular. We get this kind of like, I don't even know what that is, hexagonal like orby thing going on. But we can do less intense transformations as well. So like 0.2, and we can see kind of bigger pixels here. But basically the number we're multiplying this by is the, if you think about, say, sine wave, think about this as like the frequency of the noise. So if we multiply it by a smaller value, we take a fraction of the position, then what we're getting is a smoother piece of the gradient noise. If we raise that number higher, then what we're getting is a more choppy version of the gradient noise. So in this case, time since startup, I choose to make that 0.002. If I raise this, then again, nothing happens because I keep doing that in the init phase. Okay, if I put it in the update phase, then you can see that it looks like time is sped up. Time hasn't actually sped up. We are now just multiplying time by 21 instead of 1. So then we get the simplex noise value out of that vec3. So we get the invocation ID.x, the invocation ID.y, which are the xy positions, and we use the time since startup as the third value. So three-dimensional Perlin noise, simplex noise, gives us a value from 0 to 1 here. So then we can store that texture, or we can store the color that we created here. So this is our data. This is our RGBAU norm. The location is the XY position that we're going to store that value at. And then the texture is the image that we're going to store that color at that XY position in. You can find this in the WGSL spec. So this is texture store right here. And it says writes a single texel to a texture. If you don't know what a texel is, just think pixel. Now you can see that that's not quite true because there are texel formats. And if you go to the texel format table, you can see that RGBAU norm, the thing that we're using, is one of the texel formats that we can use. So in this case, we get RGBA. So we could do like some vec4.r.g.b or .a. And that's it. We do the same thing in both places. Because I have copied them over, I've changed the numbers a little bit, but that's the gist of it. Basically, we are taking those, we are putting the location into the noise, so the XY plus the time. We're getting a noise value out of that, and we're using that noise value to populate some color. In this case, it's kind of like the noise from 0 to 1 for R, noise times noise for G, and then noise times 0.2 for B. And then the alpha channel is always 1. But we can, of course, do whatever we want here. I could make this 0.5 and you see it darken a little bit. I think that's because the clear color right now is actually black, but I'm not sure. Can't remember. And we could also do things like instead of noise, we make this always 1 and it looks more red, maybe more like lava or something like that. But it's still fundamentally the same thing. We're just choosing colors to lay on top of these noise values. So the question then is, how do we get the time into our shader? Because the time doesn't come for free. In the future, there's a PR that may provide time to compute shaders. I believe the PR is only for mesh related things. So like only the fragment shader would get it by default, but I'm not sure. I haven't checked in on the PR recently. Time eventually is going to be a global at some point inside of Bevy shaders. But for now, it's not. So we have to do it ourselves. So the shader utils plugin is mycrate. It's the one that provides the simplex noise function. And then this is still called the Game of Life Compute plugin. I left it as Game of Life Compute plugin so that you can go look at the Bevy example. Let me show that really quickly. So here in Bevy examples, shader, compute shader, Game of Life, you will see very similar code. And I tried to leave this as kind of like straightforwardly the same as possible. So you could literally do a diff from the code that I have here against this example and see what changed. So you can see that it's called Game of Life Compute Plugin here as well. Again, if you didn't watch the other video, we went through all of the code in that for the other video. So the only system we have running here is the setup system, in addition to whatever we add in the Game of Life Compute plugin. So in the setup system, the first system that runs, the startup system, we create this new image, right? It's a 2-dimensional image with all of the values set to black and then 255. So alpha value of 1, but all black. And then we use the textile format RGBA8U norm, which is quite a mouthful. But basically, this is going to be RGB. And then we set these sizes to something arbitrary. In this case, it's 1280 by 720, but I've also done this exact same example at 4K or some other resolution. It runs well. It's really nice. One of the benefits of doing shader programming. We have to set a couple of flags defining how we actually use this image. So we get the storage binding and the texture binding for this image. And then we add that to our set of images. So at the top here, we have images, which is a mutable resource for images in the assets database. So we store the image that we've created in the assets database. We initialize a new sprite with the same size as the image. It doesn't have to be. This is just nice for us because it works out. And then we set the texture to be that image. Of course, we also set up a camera 2D bundle because we need to be able to see that sprite to be able to display it like it is on the left here. And then we take that same image and we initialize the Game of Life image as a resource with a handle to the image that we just created. So by doing this, we've created an image that is 1280 by 720 that stores RGBA values that we are storing in the assets database, and we are also giving a handle to the Game of Life plugin to do whatever it needs to do. And when we change this image inside of our shader, it will get rendered out onto the sprite because we set that as the texture. So then, of course, we have to actually define the Game of Life Compute plugin. If you haven't heard of plugins before, Bevy plugins are basically like a unit of organization of Bevy code. So if you had, say, a physics library like Rapier, you would provide a physics plugin. And that could add systems and resources and assets and whatever it needed to make all of the physics work. In this case, this is just setting up all of the processing for this image that we just created. In build here, we have our first time-related code. So we have to get the render device, so like the GPU or whatever. So we have some theoretical render device, and then we call it a GPU device, and it has some things, and we can create shaders, and it's just a nice wrapper. The buffer we're creating here is a GPU buffer, because that's what we're going to need to pass to our bind groups. So we create a new buffer with a buffer descriptor. We give it some label. In this case, it's the time uniform buffer. We make sure that it is sized appropriately. So this is going to be standard mem size of an F32. If you've never seen this before, it'll basically give us the size that an F32 takes up using the Rust standard library. So we don't have to type in some magic number, which is really nice. In this case, we want to make this a uniform. So in our shader before, we looked at it and we got time in as a uniform. So something that was read only. So we need to use it as a uniform. And I believe copy destination is something that we also need to be able to copy this from where we set it to the GPU. And then map to creation false. Gonna be honest, not really sure what this one does. I think that what it does is it doesn't map the memory to the place on the GPU that we need it at when we create the buffer, because we haven't actually passed it to the GPU or done anything with it yet. So we haven't set up that mapping, so it wouldn't be mapped. In our main world, in the world that you use, that you usually add systems to, that you usually do Bevy things in, we add an extract resource plugin for extracted time. Extracted time is a struct that we'll see later that we define. This comes before we dig into the sub app that is the render world, which is a different world. So there are two different worlds here. You cannot access everything from the normal Bevy world that lives in the render world and vice versa. So we have to make sure that if we are going to access certain things, like if we're going to add things to render stage or one of the render stages, then we have to do that in the render world, because otherwise it won't really matter, or it won't do what we're expecting and have access to the resources that we expect it to have access to. So we initialize our pipeline. We talked about that in the last video, so I'm going to skip it. We initialize time meta. Time meta is another struct that we created. So this is a custom struct. It includes the buffer that we're going to pass in, which we created earlier. We just talked about that. And the bind group. The bind group is none because, it's not in a bind group right now. We add two systems. One is queue bind group and the other is prepare time. Now in render stage, if I bring up the right page, in render stage, this is the order that the stages run in. So we've got extract, prepare, queue, phase sort, render, and cleanup. So we just looked at the time extraction for the extract time plugin or not the extract time plugin. It's the extract resource plugin for the extracted time. That will run in extract. Then in prepare, we need to prepare the time to be sent to the GPU. And then we need to queue that up with the bind groups so that it actually does get sent to the GPU. So that's what these two are doing. We're queuing it up and we're knocking them down as we need to. And then we've got the render graph here and we add the game of life nodes to the render graph so that any of this actually works at all. So let's come back to the queue bind group because that happens after preparing. In our pipeline, we do have to create a bind group layout. So to do that, we have to create a bind group layout descriptor, or basically this is going to be the layout of the memory that we're going to put in. You can see here that we've got a bind group layout entry for binding 0. That is the texture. We know it's the texture because the binding type is storage texture. We have the read write access type, which is because we're going to read and write to it, and the view dimension as well. So the same things that we specified before about the texture are being set here. And then we've got the binding 1 for the time struct in our WGSL. And we set the type of this to a buffer type. We set the buffer type to a uniform, or the binding type of the buffer to the uniform. It doesn't have a dynamic offset, so it's not like a dynamic amount of data, or it's not being placed in different places. I think actually that Bevy doesn't support dynamic offsets except for the... I'm gonna take that back. I don't know if it supports dynamic offsets. And then we've got the min binding size where we set the minimum size to the size of an F32. So we're basically just passing in the time here. The time, if it gets bigger than F32, will actually overflow, which would be a problem, but not really. So we've set the layout for the bind group data that we're going to pass in later in this pipeline. And that's basically the only differences from the way it worked before. At this point, we've bypassed a little bit of code, stuff that didn't change, stuff that is related to specifically how the texture updating works that we don't actually care about for the time variable that we're dealing with right now. So we've defined this extracted time struct that includes the seconds since startup. We get that from the time resource, which gives us seconds since startup. It's it's the same stuff. It's just a struct that we control that we can do whatever we want to. Extract resource, which is the trait that we are implementing here. So impl extract resource for extracted time is how we define how we transfer something from the main world into the render world, like we talked about. So the main Bevy world exists separately from the render world that handles all the stuff that happens with the GPU. So we have to find some way to get that data from there into the render world. This is how we do that. Then we've also got the time meta, which includes the buffer that will actually hold the sort of serialized time data, and the bind group, although I don't think we use the bind group. After we extract the time, so extracted time is set, then we have prepare time, which is a system that runs in the render world as well, and can access that resource, so the extracted time resource in this query. We get a mutable reference to the time meta, so the struct that we defined right here, and we grab the render queue. The render queue is an arc wrapper around the WGPU queue type. So if you see write buffer right here, this is a function on queue. So the queue can use itself to write this buffer at some offset with some data. So if we look at write buffer here, we are using the render queue to write into this buffer at offset 0 with this data. In this case, it's using Bevy Core cast slice, and we're using the time seconds since startup from the extracted time. So we're moving the extracted time into the buffer in a specific format. So what we've gone over so far is how we're using the time in the WGSL, how we extract the time here from the regular world that you're used to dealing with, and how we get it prepared to be put into the bind group and formatted in this buffer. Once we have all the data that we actually need, we do need to queue the bind group up to actually get sent. So to do that, we query for the time meta in queue bind group. Queue bind group, again, runs in the render stage queue stage. So we've gone through extract, we've gone through prepare, and we have all the time data, and now we're in queue. And this is actually pretty reasonable as far as these APIs go. We take the render device, the same GPU device that we were talking about earlier, where we created the buffer. We create a new bind group using this bind group descriptor. So this just describes what the bind group is going to look like. We use the layout that we already created in our pipeline. And then we also specify the data that we're going to use in this bind group. So in the other system, we set up the layout structure of the data. And here we're actually passing in the data. So our first bind group entry is the texture. And the second bind group entry, or binding ID 1, is the buffer from the meta time. And we do that as the entire binding because, we just want the whole thing. So this is how we actually get the data from the render world. So from where the time is actually running onto the actual GPU and sent into our compute shader. And again, these IDs really do matter. So in this case, we're in binding 1, which means that this is going to have to be binding 1. And because we've set this up as a buffer, this whole thing is going to come in one buffer in order. So if we had multiple fields here, we would have to make sure that they were in the right order. But in this case, we just get time, and then we can use time however we want. In this case, all we do is get time.time since startup. And since that's an F32, we can use it however we'd use an F32. So I hope you enjoyed that look into compute shaders. I'm trying to dig a little bit more into them. I want to take this a little bit further and try to do a 3-dimensional texture. But I wanted to make a video on this first because I feel like this was enough to be interesting. And y'all might enjoy hearing a little bit more about doing some advanced shader work with Bevy. Because this stuff is really cool and I really enjoy it. So I hope you enjoyed yourself, and I will see you in the next video. If you have any questions, don't forget to ask them below, and I am happy to answer anything that you have on this video or any of my other videos. I'll catch you in the next one.